Imagine a legacy, analog communications network as a highway. In a circuit-switched model, a single transmission reserves the entire route from start to finish. Because this path is a dedicated physical circuit between only 2 points, the connection is inherently secure. However, that exclusivity results in massive inefficiency. While one connection is active, all other enterprise traffic is completely blocked at the on-ramps. The packet-switched digital model solves this by shattering data into smaller fragments. These individual packets dynamically route themselves through the fastest available intersections. Moving from dedicated physical channels to shared, fragmented digital blocks solved the scaling problem of modern communications. It allowed thousands of devices to utilize the same infrastructure simultaneously. To oversee infrastructure investments at scale, an IT manager must possess a clear conceptual model of exactly how these digital crates move, both physically and logically, across a network. These blueprints govern all network communication: the 7-layer OSI model and the 4-layer TCP/IP model. The upper tiers, application, presentation, and session, handle user-facing software formatting. The lower tiers, transport, network, data link, and physical, serve as the pure logistics engine, ensuring packets reach their physical destination. This chart details the actual protocols operating within those theoretical layers. The TCP/IP suite provides the universal standard protocols, like TCP, IP, and Ethernet, that execute the work. These specific protocols facilitate everything from a small local area network in a single office to global internet communications across continents. Segmenting a network into these abstracted layers allows an enterprise to isolate problems. You can upgrade physical hardware or troubleshoot a failing connection at one layer without having to rip out and replace the entire software system. Understanding how data moves requires looking closely at the hardware governing the intersections. This diagram illustrates a legacy circuit-switched network. A continuous, dedicated physical path is locked in for the duration of the communication. This guarantees bandwidth, but forces organizations to pay for idle lines, even during moments of complete silence in the data transfer. Packet-switched networks eliminate this waste. Messages are broken down into individual, independently routed data fragments. Intermediate hardware reads the destination address on each packet on the fly. Millisecond by millisecond, it calculates the most efficient outbound route, bypassing congestion. Because these packets take varied routes, they often arrive out of sequence. The receiving endpoint is responsible for reassembling the fragments back into a coherent message. This creates massive cost savings and efficiency gains. You only utilize bandwidth exactly when data is actively moving. Packet switching provides the foundational logic that allows thousands of enterprise devices to share the exact same physical wire simultaneously without collapsing the system. But the logic of how data routes itself is constrained by the actual cables in the walls. A network's physical layout, or cable map, dictates its logical topology, the actual signal path data must follow. This schematic displays 2 primitive layouts, the point-to-point connection and the linear bus topology. The bus layout has a fatal operational flaw. Only one device can transmit at a time. As traffic scales up, this creates constant collisions, forcing devices to continuously retransmit data. This diagram shows the ring topology, which eliminates those collisions by requiring a token to transmit. However, it introduces a critical single point of failure. If the physical loop is cut anywhere, the entire network drops. Today's enterprise standard is the star topology. All edge devices wire directly back to a centrally located switch or hub in a wiring closet. This central configuration fixes distance limitations and isolates cable failures. If one line breaks, only that specific node goes offline, rather than crashing the entire department. Choosing the correct topology transforms a brittle, high-risk cable layout into a centralized, manageable hardware foundation. This diagram compares central star hardware, a legacy LAN hub left and a modern LAN switch right. A hub possesses no intelligence. It copies signals to every connected node, creating one massive collision domain where every device hears everyone else's noise. Under heavy network load, this shared transmission medium poses severe latency and constant retransmissions, crippling an enterprise network. This visual represents the solution, a Layer 2 switch, which operates intelligently at the data link layer to explicitly direct traffic. The switch actively builds dynamic address tables by reading the unique media access control, or MAC addresses, of every plugged-in device. Because the switch knows exactly which device is on which port, it isolates every physical connection into its own independent collision domain. Traffic jams are eliminated. Upgrading to Layer 2 switching replaces a chaotic shared wire with dedicated simultaneous paths for every connection, setting the performance baseline for the local network. But what happens when data must leave this fast local network and navigate the global internet? This diagram illustrates the transition from Layer 2 MAC bridging to Layer 3 network routing. The champion hardware here is the router. Unlike a switch reading local physical MAC addresses, a router moves up the protocol stack to read logical IP addresses. A router constantly queries its internal IP routing tables to perform complex path determination calculations. Using this intelligence, routers act as gatekeepers. They steer packets across entirely different enterprise subnets and wide area networks, navigating the vast internet topology. Without Layer 3 routing, businesses are just islands of hardware. Routers are the essential bridges that enable converged global enterprise communications. When you zoom out and view a complete modern enterprise backbone operating at full scale, you see these components working in concert. This diagram shows physical hardware segmented logically using virtual LANs to separate departmental traffic on the same switch. Switches use spanning tree protocol to prevent broadcast storms and maintain redundancy. Meanwhile, Layer 3 routers manage boundaries between these VLANs, calculating paths across distinct IP subnets. Network performance is not an arbitrary mystery. It is a strictly governed flow of packets managed by specific hardware at specific OSI layers. Investing in a Layer 2 switch solves endpoint connectivity and local latency. Investing in a Layer 3 router solves campus backbone logic and external reach. For IT managers, these architectural hardware choices directly dictate their ultimate return on investment, data throughput, and system reliability. Mastering this complex logistics engine allows an organization to build infrastructure that scales precisely with its data requirements.